Welcome back, everyone, to Introduction to Quantum Computing. Today we're going to talk about a brief history of quantum computing. Last time we talked about classical computing and the extended Church-Turing thesis, which suggested that all physical systems could be simulated efficiently with a Turing machine, a digital computer, and how this is probably wrong because quantum mechanical systems seem to require exponential overhead when trying to simulate on a digital computer. And around the 1980s, which is where our proper history will start, is when this was all formalized. Prehistory to this would be that people had already started to think about computing and information, processing of information as physics, and the question became, well, just use our laws of physics to derive what the limitations, the ultimate limitations within our universe are on computing. So we're thinking about computation as physics around this time. And if you're going to use physics to derive some universal rules or laws of computation, then you should probably use our best theory of physics, which is quantum physics. And indeed, the first step was to come up with a quantum mechanical model of computation. So, and all computation modeled by this Turing machine. So the first thing that was done was a quantum mechanical model of a Turing machine. Now again, this was in service of answering questions about what the limitations that the laws of physics would impose on computation. In 1985, we were introduced to a more abstract notion which would be the universal quantum computer. And that really sort of solidified this as a new model of computation. So it was called a quantum Turing machine. But it was still unclear what that might buy you. It's a new model of computation. There's some suggestions that maybe it's faster, maybe it's different in some way. But it wasn't until 1992 when we saw the first quantum algorithm. Now, this algorithm was designed to solve a problem that the algorithm would kind of solve instantly. So one run of the algorithm would solve the problem, the quantum algorithm that is, whereas a conventional classical algorithm may require many. So it was one versus many. And because it was a bit contrived, people weren't so interested in it. Also, you could show that it wasn't very robust. It's a very slightly modified problem, perhaps modified due to noise or something, and this sort of speed up kind of went away. And then in 1994 was the first time in which somebody came up with an algorithm for I'll say real problem, where the classical and quantum algorithm requires some additional resources as you increase the input size of the problem, but the classical algorithm was exponentially faster, or required exponentially less time than the classical algorithm. So this would be the first provable exponential speedup. And this was in for a model where noise was allowed. So now it's a more fair comparison in a sense. Okay, 1994, and then also in 1994, inspired by this algorithm just mentioned, is when probably the most famous algorithm was presented, and that's Shor's algorithm. Perhaps I don't need to say so much about that, but it is an algorithm that showed that factoring can be done with a quantum computer exponentially faster than the best known algorithms of the time. I see I spelled algorithm wrong. Good. So Shor's algorithm really, and of course factoring is a problem that is of interest to a lot of people, including cryptographers. So this is kind of when quantum computing really took off. But then there were still lots of questions about the efficacy of actually doing this. So the detractors kind of quickly dug in their heels and said, well, due to the intense fragility of quantum mechanical systems, such a device would not be practical. It would quickly become useless. However, also in 1995, according to my notes, was when quantum error correction was introduced. Okay, so again, at the time, people were saying, well, as soon as one error happens, basically the whole computation is dead. So, and it's practically impossible to prevent an error from happening. So there's no sense in trying to build one of these devices. A similar argument went along the lines of, it seems like these devices use sort of a continuous model of computation. So as we'll see, quantum mechanical systems have some continuity as opposed to bits, which are discrete, 0 and 1. And the discreteness is something that you want. That's why we digitize, it's why we have this digital revolution, to digitize things so that we can use error correction, so we can copy things. So if you've ever tried to, record a mixtape using the radio on an old tape deck, you'll know that every time you copy analog music, the quality degrades. But of course, you can copy CDs as many times as you want without any loss in quality at all. So the suggestion was that, well, this quantum mechanical model of computation, very similar to analog models of computation, and we already know that those cannot be error corrected. So it's likely the case that is going to happen in quantum computation. But that wasn't until 1995 when it was shown that indeed you could perform error correction using a quantum error correction algorithm. But that wasn't it. Errors would still accumulate, so one had to show that there were other techniques that could be implemented to make it tolerant to any sort of errors, and that's around the time that several groups of people threshold theorem. which says that if the noise, the process which cause errors, is below some threshold, then you can perform quantum computation indefinitely. So you can perform as long as the quantum computation as you like if the noise is below some threshold. Okay, so that was good news. And there was just one other piece to the puzzle, and that was that this can all be done efficiently. Now remember I mentioned that quantum computing has this continuity element to it, and so if I have a fixed set of quantum gates that I can perform, naively you might think, well, if I want to perform something that's kind of in between them, then I may have to use a very large, perhaps infinite number of gates. But in 1997, it was shown that, in fact, you can perform any computation, any quantum computation so anything that's allowed by quantum physics, you can do with a very, very small number of gates. So this was all that was needed to show that, in principle, we could perform quantum computation. We can do it in a fault-tolerant way, and we can do it efficiently. So that's around the time when the sort of canon was put into place, and real efforts were started to be made to actually build these devices. So that is more than 20 years ago. Today, we have devices that you can call quantum computers, but they're not going to run this Shor's algorithm, the one that kind of spurred on the field in the first place. Now, we're not going to talk about the engineering challenges in this course. We're going to talk about in the details and background that go into all of these results, and then some of the kind of what now might be called quantum programming or quantum software that sits on top of this foundation.